In this lecture, we want to talk about the procedure for hypothesis testing for a mean when sigma, the population standard deviation, is known. And what I want to talk about in this lecture is the five-step process for testing the mean, sigma known, using what's called the critical value approach. So I'm going to follow this up in another lecture talking about a different approach called the p-value approach. But this one is just a five-step process for hypothesis testing, and it's called the critical value approach. Okay, so what are the five steps here for hypothesis testing? So remember what a hypothesis is in statistics. You're going to make a claim about the characteristic of a population parameter. And what we want to do is we want to actually test that claim, okay, to see if it's true or false. So step one has two things. First thing you're going to have to do is you're going to have to define the parameter you're investigating. Okay, so this step is always going to be something like let mu, the mean, equal, and then define it. Like what exactly are we talking about? I'm gonna have three examples that you're gonna see me do in this lecture. So you're gonna define the parameter. What mean are we investigating? And then you're gonna have to set up the test. So what that means is you're gonna need to define your null statement, your null hypothesis, and you're gonna need to define your alternative. Okay, what H1 is. And now remember, at this step here, you're gonna have to pick from one of the three tests then. It either can be a right-tailed, a left-tailed, or a two-tailed test. And you know what? I have three examples in this lecture here, and so we're going to do one of each so you can see how each one is done. Okay. Honestly, a lot of times when students do hypothesis testing, if you can actually just set up the null and alternative hypothesis correctly, the rest of it kind of just falls into place. Step two. Step two is you're going to select your level of significance. And the level of significance is alpha. Okay, and it's going to be three general ones. All right, 10%, 5%, or 1%. And in this step, this will be given to you. Okay, so you're going to be given the level of significance. The next thing you're going to need to do is compute the test statistic. Okay, sorry, the extra S there. Compute the test statistic. And so we're going to denote this test statistic as Z sub 0. Okay, you'll notice that there are four things in here. Okay, I'll start with the things we should know. X bar. That's going to be the sample mean. Sigma, that's the population standard deviation. And N we know is the sample size. So what this should look like to you is a z-score of some type, actually. So the only thing that's kind of new here is we see this mu sub 0. Okay, and this is the assumed population mean. And this comes from the null. So that's where the subscripted 0 comes from. So whatever you have mu equal to up here in your null hypothesis, that's what your answer is, or that's what mu sub 0 is. So it's x bar minus mu sub 0 divided by sigma divided by the square root of it. So this is just going to boil down and just be a number. It'll be a number like 3 or minus 2. It's just going to be a number. All right, so what we're going to want to do is we're going to want to compare this test statistic to something. And that's in step 4 when we find what's called the critical value or values in critical regions. Okay, I'm going to show you where these come from on the next few slides, but where they actually come from, the standard normal curve. And so what I'm going to do is I'm going to talk about exactly what the critical values are, and then I'm actually going to give you a cheat sheet on them so that you won't have to look them up. Okay, so I'll help you out on that. And then step 5, that's going to be our conclusion step. So what you're going to do in step 5 is you have two conclusions you can make. You can reject the null hypothesis, as you see here, or you can fail to reject the null hypothesis. So what you're going to do is if your test statistic in step 3 is in the critical region that you're going to find in step 4, and I'll show you how to find the critical regions in a second, you're going to reject the null. if the test statistic is not in a critical region, okay, so if the value you have in step 3 is not in one of these critical regions, you're going to fail to reject it. Okay, so what exactly is a critical value in a critical region? All right, so these come from the standard normal curve. So we have 3 tests. We have two-tailed, right-tailed, and left-tailed tests. Okay, two-tailed test has 2 critical values, what we call z sub alpha divided by 2 and z of alpha, negative z of alpha divided by 2. So what this is here, these are called your critical values. Z of alpha divided by 2 is a z-score such that the area to the right of it here is whatever is subscripted here, alpha divided by 2. Well, remember what alpha is? I'm going to go back. Alpha is our level of significance. So what you're going to do is you're going to take the probability you would commit a type 1 error, divide it by 2, and put half that area above a specific value and half that area below a specific value. And then what you'll see me do this. After I find this value, I'm going to shade to the right, and then I'm going to shade to the left. I'm just going to take the negative of it, okay? And this shaded region is going to be our critical region. And trust me, I know you're probably watching the video and it seems a little confusing, but after you see me do an example, I promise you it's not that bad. So we have a right-tailed test. So these are tests that involve greater than. Two-tailed are, I think it's different or changed or differs. So here you'll notice there's only one critical value for right-tailed tests, and it's z of alpha. So it's just just like it is here, it's a z-score such that the area to the right is alpha. Okay, so whenever you have a right-tailed test, you don't do alpha divided by 2. And a left-tailed test, so that's your critical value, and then you're going to shade everything to the right underneath it. And this like turquoise shaded area here is your critical region. The left-tailed test is just the negative of it. Okay, it's negative z of alpha. And then the critical region is shaded to the left of this value. All right, so I'm going to give you this little cheat sheet here. Okay, so these are the common critical values, okay, for the tests. So if you see you have a two-tailed test, a right-tailed test, and a left-tailed test, you have alpha. This is your level of significance. So basically, here's what's going on. If you look back, two-tailed test has 2 critical values. If I say conduct a hypothesis test at the 0.05 level of significance for a two-tailed test, your critical values would be 1.960 and negative 1.960. Okay, if I said conduct a right-tailed test at the 0.01 level of significance, the critical value would be 2.326. If I said conduct a left-tailed test at a 0.10 level of significance, well, your critical value would be minus 1.282. Okay, so don't worry. You're going to see me do this 3 times, and we'll come back and look at this chart a lot. Okay, let's do a couple of examples here. And we've talked about this one before in a previous lecture, but let me read it again. So calcium is the most abundant mineral in the human body and has several important functions. Most of the body's calcium is stored in the bones and teeth, where it functions to support their structure. So recommendations for calcium are provided in the Dietary Reference Intakes. This is developed by the Institute of Medicine of the National Academy of Sciences. The recommended adequate intake, we call RAI for calcium for adults, is 100 milligrams per day. So a random sample of 18 adults, so this is important. So right there, the sample of 18 adults here. So just so you know what you're given as we go through, you're given N is equal to 18. With incomes below the poverty level, gave the following calcium intakes. Okay, so I've gone ahead and told you that the sample mean of these 18 adults, X bar, is 9.47.4 milligrams. And assume the population standard deviation, sigma, so giving you sigma, is 188 milligrams. Next, at the 0.05 level of significance, so now you're given alpha, right? Does the data provide sufficient evidence to conclude that the mean calcium intake of all adults with incomes below the poverty level is less than? So I want to test to see if it's less than 1,000 milligrams. All right, so first off, right here, when you see this word test, at the 0.05 level of significance, is it less than? That's telling me right off the bat this is going to be a left-tailed test. Okay. All right, so now let's jump into it. Let's see if there is sufficient evidence. Okay, so to see if the evidence is sufficient, we need to do a hypothesis test to conclude that people who have all adults with incomes below the poverty level, they're not getting the recommended adequate intake of calcium. All right, so let's go through the 5-step process for this. Okay, the first thing you're going to have to do is define the parameter. So here, I'm going to let mu equal the mean calcium intake for adults. Now, this is important with incomes below poverty level. Okay, because that's who we're investigating. Now, we knew I said it was a left-tailed test. So it's going to be mu is equal to something, and the alternative is no, mu is less than something. Well, here's what I want to do. I want to show evidence that it's less than 1,000 milligrams per day, that the average that they're getting. So I want to test to see that they're getting on average less than 1,000 milligrams of calcium a day. So then you're going to start with the null hypothesis. The assumption would be that they're getting that 1,000. Okay, so we want to test to see that they're getting less than 1,000. Let's start with the assumption that they are getting 1,000, because you have to start with some assumption. Next, it said the level of significance that's given to you, always. Next, we're going to have to compute the test statistic. Okay, so that's z sub 0. So now it's just this very simple subtraction and division problem. So it's x bar. So if you look back here, it was 947.4 minus mu sub 0. Well, that's the 1,000 right here. Divided by sigma, which is 188, divided by the square root of the sample size, which is 18. Okay, so just grab your trusty calculator for this. All right, so when you do this in your calculator, it's really important that you're going to put both the numerator and denominator in parentheses. So it's 947.4 minus 1,000 divided by, and then a second set of parentheses, 188 divided by the square root of 18. Close the parentheses. So I got the number minus 1.187. So I'll go out 3 decimal places. Minus 1.187. Okay. So next you need to find the critical values and critical regions. So what we're going to do is we're going to go back to this little cheat sheet here. Okay, and look, I was a left-tailed test, okay, and I said at the 0.05 level of significance. So you go, my level of significance was 0.05. So I'm going to go left-tailed test 0.05. It's minus 1.645. Okay, so the critical region. So what you're going to do is you look back here. For left-tailed test, this is our critical region. So I'm going to draw a normal curve, a standard normal curve. We know a standard normal curve is centered at 0. and I'm going to go to my critical value, minus 1.645. What I'm going to do is I'm going to shade to the left of it. Okay, and this in here is my critical region. Okay, so now what you need to do is treat this as a number line. Here's 0, here's minus 1.645. My test statistic is minus 1.187. So that's kind of like right here. Okay, so look, ask yourself, is it in the critical region, right? So it's not going to go past negative 1.645. So it's not in the critical region. So if our test statistic is not in the critical region, we fail to reject the null hypothesis. So we fail to reject the null hypothesis. And so what's going on here is evidence does not suggest that the mean is less than 1,000. So even though the sample mean was 947.4, it just wasn't statistically significant enough to say for sure that adults with incomes below the poverty level are getting less than the required recommended adequate intake. Okay, so in this case here, all we had to do was set up the test, compute the test statistic, compare it to the critical region, and see if we would reject or fail to reject them. Okay, let's do another one. So this example is about taller, younger women. So in the document, Anthropometric Reference Data for Children and Adults by Fryer, they present data from the National Health and Nutrition Examination Survey. Okay, that survey is done on a variety of human body measurements, such as weight, height, and size. So a half century ago, okay, U.S. women in their 20s was 62.6 inches tall. Okay, so this was 50 years ago. All right, so a researcher believes that the average height of women today is taller. Okay, so think about if you're taller, that right there, that tells me it's going to be increasing, that the height has gone up. So this is going to be a right-tailed test. All right, to test this claim, the researcher samples 25 women, so you're given, right, in their 20s, and finds the mean height, so you're given the sample mean here, to be 64.24 inches. Okay, at the 0.01 level of significance, so now you're given alpha, right? Does the data provide sufficient evidence to conclude that the mean height of today's women in their 20s has increased? So again, that's a right tail test, right, from a half century ago. Okay, it says next it says assume the population standard deviation for heights of today's women in their 20s, so you're given sigma, is 2.88 inches. Okay, so let's go through and do this. So 5-step process. Again, define the parameter. What are we investigating here? Well, if you look back here, we're investigating the height of women today in their 20s, okay? And because we want to compare that to the height of 50 years ago. So we're going to let mu be equal to the mean height of women in their 20s today. Okay, and by today I mean now, in the current year. So we're going to set up the test. It was mu is equal to something, and we're looking to say that it's increased. So mu is greater than something. Okay. So what are we going to have to assume the height is? Okay, so what was it half century ago? It was 26 or 62.6 inches tall. Okay, so we want to see that it's increased from that. So we'll start with the assumption that it's that height. We're looking to see that it's increased, so that it's greater than that height. Okay, so start with the assumption that the height hasn't changed, and we're looking to show evidence that the mean height, no, it's definitely gone up. All right, so next, select the level of significance. Well, that's given to you. It's 0.01. So next, we need to compute the test statistic. All right, so again, all this stuff is going to be given to you. X bar is 64.24 inches. So from right here. Minus U sub 0, 62.6 inches. Sigma, if you look back here, is 2.88. And then the researchers sampled 25 women. So grab your trusty calculator. So it's 64.24 minus 62.6, what it was 50 years ago, divided by, and then in parentheses, 2.88 divided by the square root of 25. Close that set of parentheses. Okay, now I know it seems silly for me to highlight this, but for as long as I've been teaching, a lot of students make errors by not including these parentheses. And you get the value 2.847. Okay, so now let's find our critical values. So our critical value, go back. So it was 0.01 level of significance, and it's a right-tailed test. So right-tailed test, 0.01 level of significance. So 2.326, that's our critical value, 2.326. Okay, so find the critical region. What you're going to do is you're going to sketch the standard normal curve, centered at 0, standard normal curve. The critical value is 2.326, and you're going to shade everything to the right. Okay, so this red shaded area is the critical region. So is my test statistic, does it fall past 2.326? Yes. Yeah, it's kind of right here. So my test statistic is in the critical region. So what do? If you look back, if the test statistic is in the critical region, you reject the null. So conclusion here, we reject the null hypothesis. And what's going on here is evidence suggests that the mean height of women in their 20s has increased from a half century ago. Okay, so for whatever reason, it looks like women are getting taller, from 50 years ago. And this is on average. Okay, so let's do one last one. So we've done a left-tailed, we've done a right-tailed. So let's do a two-tailed. Okay. So here's the next one. All right, the cheetah. It's about the cheetah. The cheetah is the fastest land mammal and is highly specialized to hunt down prey. So according to the online document, Cheetah Conservation in Southern Africa, okay, and this is by someone named Jay Urbanek, Okay, the cheetah is capable of speeds up to 72 miles per hour. Okay, so one common estimate of, not if, a little bit of a typo there, of the mean, so the average top speed of cheetahs is 60 miles per hour. So this is a common estimate. So we're suggesting that the mean top speed of all cheetahs, the average top speed, okay, is 60 miles per hour. So researchers wishes to test to see if the mean differs, okay, from 60 miles per hour. So differs. So there's a key word there. Okay, and this implies that it's going to be a two-tailed test. Okay, because I'm checking to see if it's different. Okay, so you can be different, okay, by either going up or going down. So that's why it's a two-tailed test. Okay, so to test, okay, the researcher samples, so this is what you're given. You're given the sample size of 35, and what he does is he or she records their top speeds. From the sample, the researcher found the sample mean to be 59.526 miles per hour, okay, and assume the population standard deviation for cheetah top speed is 3.2 miles per hour, or miles per hour. Yeah, sorry about that. Okay, and it says next, test at the 0.05 level of significance. So you're given alpha. Okay, so let's go through the 5 steps. Okay, step 1, let's define the parameter. So what are we investigating here? So we're going to let mu be equal to, so we're investigating the mean top speed of cheetahs. Okay, so let's set up the test. So it's a two-tailed test. So it's mu is equal to something versus mu is not equal to something. So we want to test to see if it's different from what the common estimate is, that it's different from 60 miles per hour. So we're going to start with the assumption that it is 60 miles per hour. And what we're looking to say, no way, it differs. So it's not equal to 60 miles per hour. So let's select the level of significance. So again, that's given. It's 0.05. So now let's compute the test statistic. So this is just that z-score. So it's the x bar that the researcher got, which was 59.526. And you're going to subtract mu sub 0, so that comes from the null, divided by sigma, which is 3.2, so that was given. And the researcher sampled 35 cheetahs. So in parentheses, 59.526 minus 60 divided by 3.2 divided by the square root of 35. And you should get minus 0.876. Okay, so now let's find the critical bias. So this was a two-tailed test, and the level of significance is 0.05. So we're going to go back. Two-tailed test, level of significance 0.05. It's 1.960 and minus 1.960. So it's a two-tailed test, so there are two critical values. So now you got your critical region. In this case, you're going to have two critical regions. So it's going to be centered at 0. And one is going to be way up here at 1.960. One is going to be way down here at minus 1.96. So I'm going to shade to the right. It's one critical region, and then I'm going to shade to the left. It's another critical region. So look, does my test statistic fall outside of these numbers? No, it's somewhere between 0 and 1.960. So it is not in a critical region. So when it's not in a critical region, we fail to reject the null. Okay, so there is no evidence to suggest the mean differs from 60 miles per hour. So the mean top speed differs from 60 miles per hour. All right, so I hope this helped. Seeing three examples here. So my next video will follow up to be the one about the p-value.